Well, hello friends. Today we are going to work on some I/O statistics, and I would like to make System Monitor show the amount of I/O that each thread is doing. So it's something that's not really visible to us at the moment. The closest thing we have is the syscall counter, but I would like to see stuff like, I don't know, maybe block read and write and socket read and write, something like that. So let's try to make that. And the first thing we'll do is just add some counters to the thread class. So we'll put them here next to the fault counters. Probably these should be 64-bit. So, but you know what? We're gonna have to update everything to be bigger later on. So let's just go with small for now. And we'll call this one block read bytes, maybe. Block read count and block write bytes and block write count. And we can also do the same with sockets. Because like character device, I feel like that's much less interesting, but block devices and sockets, those are the stats that are going to be interesting. Maybe we would even differentiate between IPv4, like local sockets and network sockets. I don't know, but right now, I think this is okay for now. So we're definitely bloating up the thread class here a bit, but that's going to be okay. It's okay. It's useful information. So, but where do we do something with this? So let's just put some helpers right here. I already forgot what I call them. Block. Okay, I'm just gonna take these with me upstairs so that we can see what we're doing. Okay, so we want block bytes. Oopsie. And count and write and count. Okay, not the most exciting editing going on here, but that's going to be okay. And then here we will just do a search and replace like that. Okay. That reminds me that we got to do search and replace for Hack Studio at some point. So these are the getters. Now let's also add some setters. So, or adders, I suppose. Did read. Did block read. And here we will just say the amount bytes, and we can just increment the count. Block read bytes plus equals bytes. Okay, and we'll do the same for sockets. Okay, now we want to publish this information to the outside world, so we'll do that in the proc file system. And everything's already in this huge monster of a file called proc all. That's where we have all the information about each thread. So you can see, I mean, this is one process, and then you see each individual thread in that process here. And each thread has its own copy on write faults, zero faults, syscall counts, and so on. So we're just going to put these in here as well, together with thread stats in proc all. So that would be procfs all. And here, for when we're looping over all the threads in this process, we'll just add them. block read count. Block read bytes, block write count, and write bytes. Block socket. Boom. Okay, now we have all of that, but of course we have to actually fill this in with something, so I guess we will do this in the read syscall. So what read does is, first it does all this sanity checking if we need to return some error, and then we block if we need to block, because maybe we can't read from this file descriptor just yet. And then finally we read from it. So I think here, maybe in this code here actually, we will bill it to the current thread. So the amount read is, I guess here. So if mfile is socket, if nred is greater than 0. Actually, yeah, we can fold this into a separate block here. So if nred is greater than 0, we gotta do some stuff. So this is advancing the file pointer. We have to do that. But we can also do a bunch of other stuff here. So if mfile is a socket, current did socket read, nred. And I think we can do it that way, or let's just not do that one. Leave that in, because I have to go through this at some point and fix up all of these data types. And if it's block device, we'll say did block read. Okay, and maybe we'll do the file pointer first, actually. All right, and we gotta do the same in write, so same concept. Do the file pointer first, and then if file is socket, current did socket write, and written, else if file is a block device, this is not going to be good enough, but it's a start. But I mean, regular file reads are not going to be billed this way. So actually, I think this is not the place to be doing this, actually. We should do this closer to the action. So we'll just go in socket, read, socket receive from, socket read just calls receive from. So we could bill it in here. This is where we return protocol receive. Okay. I think we're going to do it here. And received. Current did socket read and received. I think we'll do that, and we'll do this. Wait, what is this? This is receive from, right? IPv4 socket did receive. Maybe we should put it here instead. So this is like, it queues it up on the socket, but you didn't actually make the syscall to receive it yet. I think we're going to wait until you do the syscall Otherwise, you're going to get billed for stuff that you don't pick up, which might get confusing. So I think this is the better choice at the moment. And then we also have send to. We'll have and send. Current did socket write and send. Let's see. This feels vaguely okay. And of course, we're gonna need to do this for. How do we do this for disk reading? I guess when we do the inode, so maybe they're not going to be like block read and block write, but rather file system read and write. So let's change that. Instead of block read and block write, we'll call these FS. I think that'll be good. Oops. Nah. Okay. And then what do we do? I guess we would just look in inode file, because all inode read and write gets funneled through here. So here we can just do. It's just an int, but whatever. If nrad is greater than 0, then current did fs read nrad. Okay. Now we should probably go and do local socket as well, just to be nice here. So where's received from? It's here. So this is for return. Okay, and send to. Where are you sent to? Right here, okay. And in these cases, do we always succeed? Why is this written in this way? Buffer for me. Buffer for description. Oh, it's kind of backwards. This thing should really be called receive buffer for. And this one should be called send buffer for. Okay. And then here we can just do send buffer for description dot write So is st and written, if n written is greater than 0, did socket write n written, return n written. Okay, I think that's equivalent. And let's just see if any of this shows up. So this did not do well. It had some crash here. Yeah, okay, fine. Maybe I wasn't doing that right. Send buffer 4. Oh, it's supposed to switch these around. That was the whole point. Alright, so let's see what we find here. What do we want to look at? I guess Windows Server. There's a lot of socket read bytes. Block read bytes, we should change the name of that guy. He didn't read much from disk. Socket write bytes. Okay, so there are numbers coming. So let's just tweak this right here. Okay, maybe that should be called file read count and file. We'll worry about that in a moment. But right now we just want to go and add these to the system monitor. So here we're just going to add these as columns in the process model. So file read count, file read bytes, let's say, file read bytes and file write bytes. Let's ignore the number for now and let's just do it this way. So I got write bytes, okay, and then case column socket read bytes. Say socket in, or maybe sock in. Is that good? Sock in, sock out. It's going to get very crowded in that little table, but we'll see what we can do. File in, file out. I think that's maybe okay. And then do we even use these? Maybe we do. Let's just put something here. Oh, I guess this is actually for the alignment, but we want them all to be right aligned because it's all numbers. Should make this automatic somehow. Socket write bytes, okay, and then what do we actually output for these columns? Socket write bytes, socket, no, file read bytes and file write bytes. We're gonna say thread.currentState.socket read bytes, socket write bytes. Yeah, I'm changing them to file instead of fs. Okay, and I think we have to repeat ourselves with this stuff. Yeah, okay, but that's easy. Now we're gonna have to fix this data structure here, which is, this is the thing that we get, we store per process, or per thread, actually. Alright, so let's save those. And let's see, where do we actually create this stuff? Right. Here we'll copy them over from the process statistics, which is a parser of proc all. So we will just do this. State socket write bytes thread dot. Okay, and again we need to make sure that these end up in the C thread statistics that we get from the libcore procall parser. This thing is just getting bigger and bigger. At some point, I'm getting a little concerned that this thing is getting out of hand, but what are we gonna do? So we'll just say thread object get socket read bytes. Yeah, that's a pretty good name. Socket write bytes, file read bytes, and file write bytes. This is some seriously mechanical action going on here, but it's going to be good. Then I wanted to change that name everywhere. So fs read is going to be fs file read, and likewise for fs write. We'll call it file write. Okay. Now we should be able to rebuild everything and get ourselves some new columns in the system monitor, hopefully. This, actually everything turned out okay. So I really like this using JSON for the proc file system because it makes this stuff so easy to deal with, and just the debugging part of it is so nice too, because while you're working with the data you can just check the JSON, like, is this the data I'm hoping to get, instead of having to like try out your custom API or whatever and see that it returns the right stuff. You can just eyeball it. It's very convenient. And what did I want to do? And here we go. Okay. Look at all this information. So we're barely doing any file writing. Only terminal has written anything to disk, which is surprising. But it's also extremely good to know that terminal does some kind of writing to disk apparently when it starts, I guess. Why does it do that? Let's start a new terminal, see what happens. This terminal did not write to disk. Okay, so let's sort by socket. Sort of as expected, I guess. Windows Server is the most socket active because it's communicating over local socket with its client. So let's see what happens with, let's start up some the browser and then see if we can get protocol server to do some networking. So it's right here, and it has not done much socket action. This is just the IPC greeting, I guess. But now if we open up a website, and where did protocol server go? Oh, right here. And then we can see that all of the networking is billed to the protocol server here, which is really awesome. So this is him downloading all those PNGs on that web page. This is very, very cool. Sending out these little HTTP requests. I kind of want to separate this into local socket and IP sockets. I think that would be pretty awesome. So let's separate them. We'll put Unix socket read count maybe. This is going to be really sweet. I mean, it's going to get even more crowded, but it's also going to be really nifty, I think. And yeah, let's not worry about the counts so much. I think that was just for fun. The bytes is what's really interesting, I think. So I just have to update this in a billion places. And Unix socket sounds a bit more fun than local socket, because you can say like Unix in, Unix out, and it makes sense. But if you say like local in, local out, I think that's a bit more confusing, because then you might confuse it with like loopback networking, for instance. So let's just do, oopsie doopsie, let's just do it this way. Unix, and this guy right here needs to have IPv4 on these. And where else? I guess we need to do this in a billion places. So IPv4 socket, Unix socket. This was copy pasted somewhere right here. Wait, no, just the sockets this time. Boom. And likewise, we need to socket. So I think we can even say like IPv4 in, IPv4 out. That's kind of cool. That's what can we call Unix in, Unix out. Okay, and then in procfs we already did, but we have to add more here. Oopsie doopsie. Alright, there we go. Cool. And what did we forget now? Socket, read, bytes. Process model. Okay. Then this. Is this the last remaining thing? I've just been hunting these with, I don't even know how. I didn't really have any structure to how I was changing this. Hopefully we got all of the instances. Maybe I forgot something. Maybe I didn't. Oh, we did. Okay. Yeah, of course. Did socket read. So this one is going to be did IPv4 socket read. Did socket write. It's an IPv4 socket write. And did socket. Maybe we should be calling these local sockets here in the kernel context, because that's what the socket is named. That's a bit annoying. Maybe local socket should be called Unix socket instead. I like the local socket name, but it is a bit annoying that it's so similar in concept to local networking with loopback. Anyway. Oh, okay, now we are talking. Look at all these stats right here. And terminal, again, did a 100-byte write to disk. I guess that's what we see here. It's always something flushing to disk on startup. I always wonder what that was. I guess it's terminal. So this is teaching me stuff already that I didn't know. Very good. Okay, so let's do some networking with the browser. And this did not... Oh, right, this is local. I'm just opening a local file. Let's go to the Serenity website. And finally, we got some IPv4. Maybe we can sort by that. And we can see that this totally does basically what I expected, which is to bill it here. That's so damn neat. And is this thing not loading? What is this machine doing? Network task. What are you doing, network task? Okay, I think we have run into some unrelated problem here, probably. Seems like this code is just looping. I don't know why, but I don't think that's the fault of this code. So let's try that again. Browser and system monitor, and we can even thinking we can hide stuff we're not interested in. Yeah. So like, what if we don't care about virtual memory size? Something. And how did this go? Yeah. Now it's up here. Everything loaded. We reload, we can see it loading even more. Okay. This is so neat. It's like you can go over here and see it too. It's per interface, and here you can see it per socket. Oh, look at us. We are so bad. Just opening a billion sockets to the same web server. I don't think people are gonna like us doing that. We should probably figure out a way to pipeline these HTTP requests, but this is my own web server, so I'm okay with it. But that's really awesome. And sort by Unix in, we can see that Windows Server is the heaviest user of IPC, which makes sense because everyone is talking to him. It's a fair amount of data going back and forth. That's those Windows Server messages are pretty big. So if we look at whenever a Windows Server or one of its clients sends a message to each other, we send either a server message, which is 576 bytes, or a client message, which is 600 bytes. So that's why we are seeing this huge amount of IPC traffic here. Like, I mean, it's not huge, but it's you know, many kilobytes per second at least. And once Windows Server is ported to the new IPC code, then it's not going to need to send these huge messages anymore, because it will only send what's relevant for the message that it's doing at the moment. So messages will be much smaller, more compact, and we will see should see a big reduction in IPC traffic. Here we can also see that the system monitor is doing a lot of file input, which makes sense because it's reading proc all over and over, and I think that's okay that we don't have to distinguish that. it might be interesting later on to do something like here, file systems. We could log the traffic that happens on a file system, like how many bytes read and written and so on. But right now this was supposed to be about threads, and we have made some really awesome thread statistics here, I think. Maybe we should do some writing just so we can see some file writing happen. So wait, why does it not move? Just move, jerk. Wait, my window moving shortcut is not working. Now it is. Okay. I don't know what that was. Okay, so let's build a little rainbow program I have here. And I did not see any file I/O. It's weird. I just want to see some file I/O, dude. Is that the wrong sort order? Why did this not log anything? Hello, Boo. Did the shell get built for this? We'll just save this here. Okay, so this guy got built for it, the text editor. But why did we not get built for sending the output of echo somewhere? What about do something big like that? Is cat maybe, I guess, get built for it and then we never see that? So what if we just cat dev random to dev null? Okay, I don't know how I managed to do that. Where's cat? Right here. It's not doing any file I/O. Why is that? I guess oh, it's not an inode file. We open the device directly. So we have to save it to a file. Maybe this should be called inode in, inode out. File in, file out is okay for now. Okay, what if we save to a file? Okay, well, system now very upset. Okay, I didn't mean to hurt you. Okay, I guess this is not something that we are very good at dealing with. How do I stop this? Oh, well, here we can see it certainly writing to file. Stop. Okay, can we use the kill function here maybe? Okay, we're gonna have to get better at this situation for sure. Why is this so slow? Maybe forking is really slow right now? It's really strange. Anyways, we are learning that we definitely have a performance pathology right here. Cat dev random to a file in the system, it becomes very unpleasant. Okay, did that kill it? I think maybe that didn't kill it. Oh well, whatever. We don't have to do that. We can just kill the thing. So at least we saw that file I/O was happening, and it's getting built to the thread that's doing it. So when you do this short-lived stuff like echo something to a file, then echo is going to get billed, but echo dies right after, so you can't really see that it happened. But I think that's okay. So I would say we're pretty good here, so let's just commit this. Yeah, I'm okay with the names. Local versus Unix socket, we can live with that for now. Kernel plus system monitor. Log the amount of I/O. Log some log amount I/O per thread. This patch adds I/O counters to each thread. File inode file read count. Bytes. Unix socket read count. Okay. And I already feel like I don't need the count, so let's just get rid of those. These are then exposed in proc all and seen in system monitor. Thanks to this, well, whatever. That's cool. Let's get rid of those counts, because they're just, since we're not showing them anywhere, they're just bloating up the data structure anyway. Cuts it down to half size. And let's see. Count. We can get rid of them here too. Yeah. Okay, let's see it. Boom. Boom. Look at all those counts. I mean, byte counts. So who reads the most? Windows Server. I guess it's reading this thing right here. So every second we will read proc all to produce this. But System Monitor will speed ahead because System Monitor is also fetching like stack traces and stuff. It's a bit sad that Windows Server has to read this growing JSON file once a second to produce the CPU graph. We could probably do better, although ultimately I would like to move this graph out of the Windows Server anyway and have it run as like an applet, and then applets would be able to register like a graphical surface and then inject that into the menu somehow. I'm not exactly sure how that should work, but I know that Sergey expressed some interest in that, so maybe he has some good ideas, who knows. But right now, I'm pretty happy with this, so let's just amend that last commit with removing the counts. And then we can just push this, or, I mean, we don't have to push right now, but I think that's good. So, yeah. I think I'm going to end the video here for today. So if you made it this far, then I thank you for watching, for hanging out, stopping by, while we continue into the month of December with this operating system. And I guess we'll see what happens next. Hope you saw something interesting, and I will see you next time. Bye. Look at that.